Welcome back, and this is the last in the videos looking at the electron structure. So far we've looked at electron configuration and how the electrons are arranged in atoms and ions, and that's very important because it's that electron configuration which underpins the chemistry of the elements and their ions. In the second set of videos we looked at ionization energies, and we looked at ionization energies going across a period and down a group. In this last video, what we're going to look at is successive ionization energies. And that basically means taking a single atom and stripping it of its electrons one by one, and having a look at what the energy required to do that can tell us about the electron structure. So we're on page 22 of your notes, and we're looking at these successive ionization energies. So that's the energy required to remove one electron after another, in other words, successive electrons from one mole of gaseous atoms. So here we're taking a single atom or a mole of atoms, and we're looking at what happens when we remove the electrons. When we do that, we get a plot that looks a little bit like this. So along the bottom we have the ionization number, and up the side we have the energy required to do that. So the outer shell electrons, well, those are the easiest to remove, and the inner shell electrons are much harder to remove. What you should notice is a couple of things. Firstly, there's a gradual increase, but then there's a massive jump. And this jump is important because it tells us that the electron being removed between 6 and 7, this 7th electron is coming from a shell much closer to the nucleus. So these are probably your outer shell electrons, and then you're going to go in a whole shell to remove this 7th electron. And it tells us that we have 6 electrons in the outer shell, because there's 6 electrons, relatively straightforward to remove, and there's a big jump to the 7th. So let's have a look at what that looks like for phosphorus. So here we have a dot cross diagram for phosphorus, and we have the ionization energy to plot beside it. So here, number 1, that's the first electron being removed. Well, that is the outer shell electron. So one of these outer shell electrons being removed. And then I have 1, 2, 3, 4, 5 electrons here being removed. And that is telling me that I have 5 electrons in my outer shell, because once all those electrons have been removed, the next electron has to come from a principal quantum shell closer to the nucleus. It's lost a level of shielding, so it's going to have a much stronger electrostatic attraction between it and the nucleus. So that's where this jump comes in. Then we have another 8 electrons. They are here, and those represent the 8 electrons in this middle ring in principal quantum shell 2. And then there's another big jump here between the 13th electron being removed and the 14th electron being removed. That's because the 14th and the 15th electrons being removed are these electrons here, and these are the 2 electrons closest to the nucleus, so they require the most amount of energy to remove. So we can do the same for magnesium. Here you have these 2 electrons being removed first. So these are the first 2 electrons being removed. Once they're removed, we've got this big jump up to the next 8 being removed, and then another jump to the last 2 being removed. Notice there is also this gradual increase. So it gradually becomes harder and harder and harder to remove these electrons, even though they're coming from the same principal quantum shell, they're experiencing the same shielding, and so on. The reason for this is because you're trying to remove an electron from an increasingly more positively charged ion. So getting an electron away from a neutral atom is hard enough. Trying to remove it from an ion, which is 2+, 3+, 4+, and so on, it becomes increasingly more difficult. So the jumps indicate that you're moving between principal quantum shells, and this gradual increase tells you you're trying to remove an electron from an increasingly more positively charged ion. Aluminium is the same, so you've got 1, 2, 3, jump, and then your 8, and then your last 2. So there's a slight difference here because this first electron is being removed from a 3p subshell, and the next 2 electrons from a 3s subshell. Last but not least, potassium. Now potassium has 4 shells of electrons, so we have the first electron here being removed, which is being removed from an outer shell furthest away from the nucleus. Once that electron is gone, you've now got to break into the next principal quantum shell, which is closer to the nucleus. There's that gradual increase as you're taking away an electron from an increasingly more positively charged ion. Another jump as we go to the second principal quantum shell. Again, that gradual increase. And last but not least, the jump to the 2 electrons in principal quantum shell 1, closest to the nucleus, requiring the most amount of energy to remove. So you'll go at practicing this now. What I'd like you to do on a piece of graph paper is plot the electron being removed, in other words, the ionization, versus the log of the ionization energies. Now we use logarithms rather than the actual numbers because the range of the numbers is too large to fit onto the graph paper. The difference between the first and the last ionization energy is just too big. The range would be too big. So we plot logarithmic values so they fit nicely on a graph paper and so we can actually see the pattern more clearly. So what you should see in your graph is a gradual increase. As we said, this is due to the electrons being removed from an increasingly more positively charged ion. The jumps in the calcium graph, well, there should be 3 of them. The first one between the second and the third electron being removed because the second electron is in a 4s subshell and the third electron is in a 3p subshell. The second is as we're moving from 3s to 2p, and the last is when we're moving from 2s to 1s. So the closer you are to the nucleus, remember, the harder it's going to be to remove the electron, the stronger the electrostatic attraction between that electron and the nucleus. Along with ionization energies across a period and down a group, successive ionization energies also help us to provide evidence for the existence of principal quantum shells. If there were no shells, there would be none of those jumps. There would just be a gradual increase as you remove electrons from an increasingly more positively charged ion. The jumps exist because the electrons are being removed from shells which are becoming closer to the nucleus with less shielding. That finishes part 2, looking at ionization energies. And just as for part 1, we'd like you to do a revision page. In normal times, we just ask you to do a revision page. Here, we're giving you some guidance and some guidelines, but you should be able to do this yourself from now on using the specification terms on the front cover of the packs. So for each specification point, you need to make yourself a little note. Could be in the form of a flashcard or it could be in the form of a revision page. So that finishes these notes on electron structure. Electron structure is incredibly important in chemistry because it is the electron configuration that determines the chemical properties. By knowing the electron configuration, we can work out what kind of reaction the atoms and the ions are going to undergo. So that's all for now. Take care. See you soon. Bye-bye.